So welcome back to the aerodynamics class. Today we will be discussing an interesting topic called thin airfoil theory. Right? So I acknowledge fundamentals of aerodynamics by John D. Anderson. Right? So we will be starting our discussion now. Right? So you know already that the flow over any body, the lift can be calculated based on the circulation around it, right? So now our idea is to apply this for the airfoil, right? Because airfoil is of primary interest in the aerodynamics or in aircraft related discussions, right? So in general, the basic equation necessary for the calculation of airfoil lift and drag moments, whatever it is, we used to use initially the symmetrical airfoils, and hence we will use the symmetrical airfoil in our case. Now, to start with, let us consider, because in the last few classes we had enough discussion on vortex sheet. So anything based on the discussion of vortex sheet, we are aware, right? So let us start. Consider a vortex sheet. So I will write, right? Consider a vortex sheet. Okay. So I want to consider a vortex sheet on the camber line of the airfoil. So let me draw the camber line. Say I have an I have an airfoil. Say I write this is X and this is Z, and I draw a camber here. Okay. And I consider a vortex sheet on the camber line. Okay. Please follow and please derive with me. Camber line of an aerofoil. Right. So here, so this is a camber line. Okay. So let me say this is a camber line. You know what is camber line, right? Camber line. So we can say that this is Z is equal to Z of X. So I want to have a vortex sheet on the camber line. So let me have a vortex sheet on the camber line. Okay, and we can say that this is S, and the elemental distance is a ds that you already know. And if this is a camber line, then one can say that this is chord line, right? Chord line. So the total distance is C. Okay. And let us assume V infinity, that is free stream velocity, and the angle of attack alpha. The angle of attack is the angle between the free stream velocity and the chord line that we already know. Right? So here x-axis is the line along the chord line, and z-axis is perpendicular to the chord line, right? And the distance measured along the chord is denoted by S. You see the distance from here is S. Okay. And the shape of the camber line is given as Z equal to Z of X. Okay. Now, here let me say a small component. Say here the W dash is the component of velocity, right? Let me say W dash is the component of velocity normal to the camber line. So as an aerodynamic student, one can say that the W dash is equal to W dash of S, because this can be along the camber, right? So now we will have some consideration, right? So please take it. Now let us view this particular vortex sheet, right? I make some assumption here, right? This is X and Z. So the distribution of vortex sheet over the surface of the airfoil, and when it is viewed from a distance, it looks like almost the same as the vortex sheet placed in the camber line. That is what our idea, basic idea. Now, let us stand back once again and consider that the airfoil is so thin. Okay, that is what here it becomes, thin airfoil theory, right? So let us consider the airfoil is so thin that the camber line is very much close to the chord line, right? So one can say that the camber line, of course, say this is the camber line, and now I say that the vortex sheet appears on the, not on the camber line, but on the chord line, right? So we orient our thinking in such a way that the vortex sheet is placed in the chord line now, right? And of course, this is the camber line. So please note. And this is somewhat true in the case of symmetrical airfoil. Your camber line and chord line will become same, right? So we can say that this is, of course, yes, the camber line Z equal to Z of X, and this is W dash of S, and again you have V infinity, and this is angle of attack alpha. And as usual, till this point is the chord line C, right? So this is the vortex sheet on the chord. Vortex sheet is, please note, vortex sheet is on the chord, right? Vortex sheet is on the chord. Vortex sheet is on the chord line. So now one try gamma, right? So we can say that gamma is equal to gamma of x. So we still wish to have the camber line to be a streamline for the flow, right? We can keep the camber line, but we will assume that the camber line is a streamline for the flow, right? And the gamma is equal to gamma of x, and the thing is, one can say that this also can satisfy Kutta condition of gamma of c that is equal to 0, that you already know. In the last class we were discussing about the Kutta condition where gamma of the trailing edge is equal to 0. So the strength of vortex sheet on the chord line is determined such that the camber line is a streamline, right? So let us consider that. So please note all these points, and we will be deriving the equation now. Right? Now, for the camber line to be a streamline, the component of velocity that is normal to the camber line, right here, normal to the camber line must be 0 at all the points along the camber line. So the velocity at any point in the flow, right? So we can write the velocity at any point in the flow is the sum of the uniform free stream velocity and the velocity induced by the vortex sheet. So let us write, I write here V infinity, right, plus dash of yes to 0, right? So the velocity at any point in the flow is the sum of uniform free stream velocity and the velocity induced by the vortex sheet. So here we will consider V infinity. So I write this as V infinity comma n be the component of free stream velocity normal to the camber, right? Please note the free stream velocity normal to the camber. So for the camber line to be a streamline, we can write V infinity comma n plus W dash of S is equal to 0 at every point along the camber line. Now, say let us draw it once again. Okay, X is that, and say this is the camber line, right? And I consider any point. So I say this is say V infinity, right? And hence this become angle of attack alpha, right? V infinity, and so this is a camber line. So we write z equal to z of x, right? Then say here I draw here perpendicular line, right? And the perpendicular to the camper line, and this is perpendicular to Z. Right. So here you have a small the elemental distance, so that can be taken as a dz, right? And I draw a line parallel to x, right? So if I write a parallel to x, then this becomes alpha. And if I want to have a 90-degree here, so I can draw this, and this we need to calculate this angle, and here this angle need to be calculated. So this we can say that this is a dz, right? And this can be in x, right? So this is a dx. We can say this is a dx, and the one perpendicular is v infinity comma n, right? So one can write the velocity here can be v infinity and comma n, which is perpendicular, and the one which is parallel to x can be considered as x or dx, right? So now this angle need to be calculated, right? So let us say if this is angle theta, then we can say that this can be dz and this is a dx. So one can write this angle is equal to, say, tan inverse of dz by dx. So now at any point P, so this is the any point P in the camber line, right? Any point P in the camber line, see, we can calculate the slope. The slope is dz by dx, correct? Any point in the camber line, we can say dz by dx is the slope, and hence we can write the v infinity comma n can be expressed as v infinity sine alpha, this is alpha, plus tan inverse of minus dz by dx. So so we have a minus here because it is in the reverse, right? So here we determine the component of free stream velocity normal to the camper. So please note that the free stream velocity normal to the camper is calculated here. The free stream velocity normal to the camper line, that is v infinity comma n. So we have arrived to v infinity comma n, that is equal to v infinity sine alpha plus tan inverse of dz by dx. Right. we can go to the next point. And please note always here the alpha is expressed in radians, right? All the angles are expressed in radians. Okay. Now, let us consider here for a thin airfoil, here the assumption is for thin airfoil, and we consider the alpha is very small, right? Then we have a tan inverse of minus dz by dx that has a very small value, and we can write also based on the trigonometric relation sine theta is equal to tan theta, which is almost equal to theta, and hence v infinity comma n can be written as v infinity alpha minus dz by dx. Please always remember dz by dx is the slope of the camber line, right? Now let us develop the expression for w dash of x, right? Because you know very well that the v infinity n plus w dash of s is equal to 0. So we have already calculated v infinity n, and we need to develop the expression for the w dash of s in terms of strength of vortex, right?
Sir, excuse me, sir.
Yeah, please.
I didn't get the minus symbol. I mean minus dz by dx. How the minus came? Could you say once?
Yeah. So here the dz by dx, right? So we consider that in the other direction. If it is above, we can consider in the different way, and if it is in the other direction, and hence we consider the minus, the dz by dx, the slope. Say for example, if you want to have a slope here, and if you want to have a slope here, it is different, right? So for that reason, we use minus, and otherwise it is not necessary to consider.
Yes, sir.
Yeah. Now, the W dash is again an important point we need to develop. So let us develop. So the expression for W dash now. Expression for W dash of S in terms of strength of vortex. Right? So in all our discussion, we have mentioned that the W dash of S, and then we have made an assumption that the velocity, the W dash is an induced velocity, and then as the airfoil is so thin and the camber line is close to the chord line, so I denote here, since the camber line is close to the chord line, I write W dash of S be W of S. Not W of X, but W of X. Because, okay, I will draw that once again here. this is Z, and here you have X, right? And already I said the vortex sheet is in the chord line, and say we consider a elemental vortex, right? And the elemental vortex of strength here, gamma into d zeta, I consider zeta can be x comma zeta here. It is also in the x direction. So we consider zeta as another term in order to represent the strength of the vortices, right? So say for example, from here, I say it goes, say an elemental distance. So I will take this elemental distance as d zeta, and we already know the total distance is x, right? And assume that the induced flow W is at x, and the elemental length d zeta is at zeta, the distance zeta. So I include a new term zeta here, right? So please note this W dash of S, which I considered for the camber line. Now I consider it for W of X, right? So please note that consider an elemental vortex of strength gamma d zeta, located at zeta from the origin. Okay, zeta from the origin. Now gamma is equal to gamma of zeta now, right? And you know already the velocity, induced velocity dv is equal to minus gamma ds by 2 pi r. Okay. So let us calculate the induced velocity at the chord line, right? What is the induced velocity? This W is the induced velocity. V infinity n is the velocity normal to the camper, and W is the induced velocity in the chord. So let us write the velocity dW. Let us write the velocity dW at point X. Please note dW at point X induced by the elemental vortex, at point zeta is now given by dW, that is equal to minus gamma of zeta into d zeta by 2 pi x minus zeta. So please always remember this equation. dV is induced velocity, that is equal to minus gamma ds by 2 pi r. So this calculation where we have considered here it is 0, and this is induced because of x minus zeta, and now at leading edge, let us say at leading edge. What is that at leading edge? What is the value of zeta at leading edge? What is zeta at leading edge? What is this zeta at leading edge?
0.
0. And what is zeta at the trailing edge? Zeta at leading edge is equal to 0. At the trailing edge,
Equal to chord length.
equal to chord length. So I write here, I integrate it for the whole chord length, that is equal to, say I write it as w of x minus integral 0 to c gamma of zeta into d zeta by 2 pi into x minus zeta. Right? So we have arrived to w of x. Now, we already know that the boundary condition necessary for the camber line to be a streamline, right? The boundary condition necessary for the camber line to be a streamline, then we will arrive to the equation v infinity comma n plus w dash of x s is equal to 0. So we can arrive that. So please note the equation, the final equation. The boundary condition necessary for the camber line to be a streamline. The boundary condition necessary for the camber line to be a streamline we can write v infinity comma n. So v infinity comma n can be written as v infinity into alpha minus dz by dx plus, so we have a minus, right? Integral 0 to c and gamma of zeta d zeta by 2 pi x minus zeta, that is equal to 0. Or one can write 1 by 2 pi integral 0 to c gamma of zeta d zeta by 2 pi into x minus zeta, that is equal to v infinity, that is equal to v infinity into alpha minus dz by dx. So this is the fundamental equation of the thin airfoil theorem. Fundamental equation of thin airfoil theory. right? Now, so I stop at this point for the today's discussion, but one single question. I said the camber line and dz by dx is the slope of the camber line that you know, right? Now, when there will be no camber line, when the camber line has no effect, at what condition?
If the airfoil is symmetrical, sir.
Yeah, so if the airfoil is symmetric, then what happened to this term? Dz by dx?
Becomes 0, sir.
Yeah, becomes 0, and we can reduce this equation to 1 by 2 pi integral 0 to c gamma of zeta into d zeta by 2 pi x minus zeta, that is equal to v infinity alpha. Okay, so I stop at this point for the today's discussion, and we will continue further in the next class. So yeah, thank you.